Okay, I guess we'll get started. How's everyone doing?
Okay.
Better? Good? Yeah.
Do you have a rule of thumb for which we can determine the null hypothesis and the alternative hypothesis? Because I was having trouble just figuring out which one.
Yeah, we'll go over that today. Chapter 20. Did the homework go okay? Were you guys able to get to it? I hope. Okay. All right. So we're going to continue on with hypothesis tests, and so yeah, the book splits up all these topics into chapters of about equal size. But hypothesis tests, chapters 20, 21 can probably be one chapter or one concept together, but they've split it up here. Well, I guess you can only talk about lecture for an hour, I guess. So anyway, so let's talk about figuring out the hypotheses when we are doing a hypothesis test. Okay, so we're still working on hypothesis tests, and we're dealing with one categorical variable. So we might call this a one proportion z-test. Okay. The idea here again is that we're dealing with a single categorical variable. And so with a one proportion z-test, your null hypothesis is always going to be that p is equal to some value. So I'm just making up some value, 30% or whatever, but so the null hypothesis is always going to say that p, the population proportion, is equal to some value. And we refer to that value as p hat. Not p hat, p0, okay? Some value p0, and in this case p0 is 0.3. Okay? The null hypothesis will always have an equal sign. Just remember that. It's always going to be equal to something. And when we're dealing with one categorical variable, it's always going to be p, the population proportion, is equal to some number. And you got to read the problem carefully to figure out what that number should be. Okay? As a rule of thumb, that number is almost never going to be your sample proportion. Okay? So p0 is almost never equal to p hat. So as you're reading a problem, a lot of times it's easy to pick out what p hat is equal to. Okay, p hat is your sample proportion. As you're reading the problem, a lot of times you can figure out what p hat is. Okay, so p hat is generally easy to identify in a problem. Okay, p hat comes from your data. So almost never will you say that the null hypothesis p is equal to whatever p hat is. Okay, so if you take your data and you get that, 27% of people in your sample is this, your null hypothesis will probably not be p is equal to 0.27, okay? And I'd say that's like 99% of the time. Very, very, very rarely will you have p is equal to whatever p hat is. Okay. So as you're going through a problem and you're trying to figure out your null hypothesis, usually there will be two proportions listed in there. One proportion is your p hat, okay, and then the other proportion is going to be your p0. And that's the number you would use in your null hypothesis, okay? So for example, I might say pollsters want to know if a certain candidate will win the next election. Okay, they survey 600 random voters and find that 320 say they will vote for candidate A. Does this provide evidence that candidate A will win? Or maybe I should write will win with the majority. So in this case, we want to set up our hypotheses, and let's just figure out what our null hypothesis should be. Okay. So our null hypothesis, because we're dealing with one sample, and it's a categorical variable, they're either going to vote for candidate A or they're not, our null hypothesis is going to have p equal to some value. Okay? As we go further on in the course, we will learn about hypothesis tests with two samples, hypothesis tests with numeric variables, okay? And that will change the symbols that you use in your null hypothesis. But right now we have one categorical variable, so we've got one proportion, and it's going to be, the null hypothesis is p is equal to something, okay? So what proportion can we pick out in our problem?
45.
Yeah, so we have 320 out of 600, but this is our p hat. P hat is equal to 320 out of 600. Okay? And there's another proportion that it's not explicitly stated, but it's implied in here, okay? And what is that? It says, we'll win with a majority. Okay? So in order for candidate A to win, he or she needs over 50% of the vote. Okay? So our null hypothesis is going to be that p is equal to 0.50. Okay. The alternative hypothesis will then be, the alternative hypothesis is in the exact same form as the null hypothesis, except you change the equal sign to something else. So it's going to be p something 0.50. Okay? And so do we want to see if the proportion is greater than 50%, less than 50%, or not equal to 50%? Greater. So we want to know if he will win with a majority or she will win with a majority. So we're going to put p is greater than 50%. Okay? So when picking out the alternative hypothesis, is in the same form as the null hypothesis. Okay, but instead of the equal sign, the null hypothesis always has an equal sign. Use greater than, or less than, or not equal. And so your choice of greater than, less than, or not equal will depend on the phrasing of the question. Okay. So we call, if the hypothesis test, if the alternative as greater than or less than, we call this a one-sided test. Okay? This is called a one-sided test. Sometimes it's called directional test, or one-tail test. They're all saying the same thing. Okay. You read the question, or read the problem, and you will look for keywords. Keywords like, you know, is there evidence that ... is, you know, greater, larger, more, bigger, etc., 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 okay? Or on the other hand, less, smaller, fewer, things like that. Okay? So words that imply that the thing that you're looking for, you want to know if it's on one side, if it's greater than the thing, or if it's less than the thing, okay? So then your alternative hypothesis will be P is greater than, you know, some number. Whatever it is, okay, P0. Okay, and on the other hand, if the alternative has a not equal sign, this is a two-tailed test, or two-sided test. Or we might call it a non-directional or two-tailed test. Okay. And the problem will have words like is different, has changed, not the same. Things that don't imply that it is bigger or that it is smaller. It's just, is it different, okay? That's things like that, okay? And sometimes, you know, it won't have explicitly written this, but you've got to figure out what is going on. Okay, so let's try another example here. All right, so we'll say researchers want to know if there is a difference between the name brand drug and the generic one. Okay. I'll say it is known that patients show, I don't know, a 57% improvement rate when using the name brand drug. 400 patients. Did I just write patients like the virtue? Okay. 400 patients are given a generic drug and 205 show improvement. What do these results tell us? So we have a null hypothesis and an alternative hypothesis. Okay. So again, well, just because we're in this chapter, you know that we're dealing with one proportion, one categorical variable. And what is that proportion or categorical? So P is the proportion in the population, but what does this P represent? It is the proportion of
the improvement rate.
Of the improvement rate for
Those using the drug.
people who use the generic drug. Okay, so P is the improvement rate of generic drug users. And we want to know, is this what? How does it compare to the name brand drug? Okay, and so what does our problem say? It says researchers want to know if there's a difference between the name brand drug and generic one. Okay, and what is the proportion that's been established for the name brand drug? 57%. Okay, so we want to know, is the proportion of improvement, is the improvement rate for generic drug users, is that the same as the name brand one, or is it greater than, less than, or different from? Different. Okay, so our alternative is going to be that P does not equal 0.57. Okay. Is that all right? Okay. And then when we go through the problem, what do we do? So I hope I asked Romelin to cover some examples like this in lab section. So you go through and you look at your data, and your p hat would show 205 divided by 400, and so you would have what is that? 0.5125? I don't know, something like that. Okay, and then and you want to know, is that significantly different from 57%? Okay, so your z-score is going to be p hat minus the value in the null hypothesis divided by the standard error. Our standard error is p0 q0 over n, so we use 0.57 times 0.43 divided by 400, and we get this, and we plug that into there. Okay. And then whatever our z-score is, we go to our z-table, and we look up z and both the plus and minus versions of z, okay? Because this is, we have a not equal sign, we have a two-tailed test, so our p-value is the total area in both tails. Okay, because we have a two-tailed test, or the alternative has a not equal sign. Is that comfortable? Yes.
So how do you get two z-scores then? Or do you just
So you just get a z-score, and then you take the one you take the positive and one you take the negative. Okay. So basically, you just look up the area of one tail, and then you multiply it by 2. Yeah.
So why are both z-scores negative? Oh.
Plus and minus. Okay. So whatever your z is. But that only applies when you have a not equal sign. Okay. Yes.
So what z-score do you take when it's like greater than?
Okay, so when it's greater than or less than, okay, so if it says researchers want to know, let's say if the generic drug is more effective than the name brand, or generic is less effective than the name brand, that will affect how your alternative hypothesis is written, okay? So if you have the alternative shows that P is greater than 0.57, then you take the area to the right of your z-score. Okay, so wherever your z is, you take the area to the right. If the alternative says P is less than 0.57 or whatever it is, whatever your z-score, you take the area to the left. Is that good? So, if you have P greater than, you take the area to the right. If P is less than, whatever your z-score is, you go in the opposite direction. If we're not equal to, you just find the tail. So, you always go, the tail is always the direction away from the hill. So if your z is positive, you're going in that direction. If your z is negative, you go in this direction. And then for the two-tailed test, you double it. But I'm hoping the calculation part and looking that up in the table feels somewhat comfortable for you guys. Okay, and I'm hoping you guys got some practice in lab section and also with your homework the past couple days. Okay. So let's talk about p-values. And what our p-values mean, okay? So what is a p-value again? The p-value is a probability, okay, is the probability of observing our data, or something more extreme, if we assume that the null hypothesis is true. Okay? So in this hypothesis test over here, we're assuming that the improvement rate of the generic drug is equal to 0.57. We're assuming that people who take the generic drug have an overall improvement rate of 57%. And we're asking, okay, when I gave it to 400 people, only 205 improved, which is lower than my 57% rate. Okay, so we're asking, what's the probability of seeing something this low or something more extreme? And that's why we have a two-tailed test, because technically, if the null hypothesis is true, we expect p hat to be close to 0.57. So 0.57 goes in the middle, and what we observed, okay, we observed p hat equal to 205 over 400, so 0.5125. So that's down here. So we want to know what's the probability of seeing something as unusual as our data or something even more unusual or more extreme. So we're going to do 51.25% or anything lower. But equally interesting would be something that is that much or greater. So this is about, about 6 percentage points lower, 5.75 percentage points lower than what we expected. So we would be interested in what happens if we were 5.75 percentage points higher. So we would go up to, what is this, 0.6275 or higher. Okay, and so both of these are equally interesting. And so our p-value is the total probability of getting something at 0.5125 or lower, or 0.6275 or higher. I should have picked easier numbers so I don't have to deal with all of this stuff. But if we were just dealing with 51% versus 63%, okay? If we were seeing a 6 percentage point difference, we just want to know, our data showed us a 6 percentage point difference. We want to know what's the probability of seeing, getting a random sample where we are 6 percentage points lower or something more extreme, or getting 6 percentage points higher or something more extreme. And that applies when we have a not equal sign. Yes?
So what you just did there is for the name brand drug, or is that trial for?
So no, it's all for the generic one, okay? So the generic drug, we don't know. We want to know if there's a difference between the name brand drug and the generic one, okay? And we know somehow, okay? We know that the name brand drug has a 57% improvement rate. What we want to know is the generic drug just as effective? Okay? And so what we're trying to study is, what we're trying to figure out is the improvement rate of the generic drug. Okay? We're going to start off with the assumption that they're equally effective, and we want to know if our data reveals something contrary to that. So if this is our assumption, then that means when we take samples of data, our sample proportion p hat should be close to 57%. When we took the data, we didn't get 57%. Let's just say we got 51%. Okay, 51% is lower than 57%. 6 percentage points lower. Is that a big deal, or is it not that big of a deal? Well, it depends on the standard error, and so we do the math. Okay, but the resulting question, or the answer that we're going for, the p-value, is, what's the probability of observing our data or something more extreme if the null hypothesis is true? Okay, so if this is indeed true, and any time I take a random sample, I might not get exactly 57%. Maybe I'll get 53% or 60% or whatever. Okay, but I got 51%. So does that happen quite a bit, or is that a rare occurrence? That's what we're asking. And so we do this, and we find the probability, the total probability of getting something of a 6 percentage point difference lower or 6 percentage point difference higher is going to be my total p-value. Okay, so it's very important that we can that we understand what a p-value is. Okay, so let's say I haven't done the math, but let's say the p-value ends up being 0.02. Okay, so that means if the generic drug truly has a 57% improvement rate, how often will I get a 51% improvement rate in a random sample of 400 people? Well, it could happen, right? I could just get unlucky in my sampling procedure because it's random. I could be unlucky and see only 51%. But how often does that happen? That only happens 2% of the time. Okay, so let's say the p-value is 2%. That means if p truly is 0.57, okay, then when I take a sample of 400, people, I might get a sample proportion of 0.5125 or lower, or let me just write, or more extreme, by random chance alone. Okay, just from the nature of random sampling. But that happens only 2% of the time. So we're faced with a choice. Do we say, well, maybe I was one of the lucky 2%? Or do we say, I'm probably not one of the lucky 2%, and probably my initial assumption is wrong? We have to make that choice. Okay. Rule of thumb, we'll say if it's less than 5%, we generally say we're not that lucky. My assumption was probably wrong. Okay, but right now I'll talk about, when should we pick a large or small alpha or significance level for making that decision. And I want to make sure this is okay before I move on. Yes?
Can you repeat the rule of thumb you just said? If it's less than 5%.
5%, okay? So if it's less than 5%, we generally will choose to reject our initial assumption or reject the null hypothesis. And if it's greater than 5%, we'll say I'm not ready to reject it, okay? But I'm gonna talk about that right now, okay? Well, in greater detail. Yes?
So then is it necessary to calculate your z-score?
Well, in order to get this p-value, you need a z-score. This p-value results is the area in the tails. And to get the area in the tails, you need the z-score. I just said, to save time, I skipped the math and I just said, let's say we got this as our p-value, okay? But to get here, I would have needed a z-score. Yes?
So to get to your p-value, you added up the two tails?
Yeah, so to get my p-value, I found a z-score. I looked up the z-score in the table, and I found the tail area, and I added those two tail areas together. And that's my p-value, okay? But I just made this up, okay? So when you go through the math and you find out that it's not 0.02, don't be confused. I'm just trying to save time to illustrate the meaning of the p-value. Okay? And you know, if the p-value is 20%, this statement is still true, and it's just maybe instead of writing, but that happens only 2% of the time, we'd say, and that happens 20% of the time. Okay, so you would say that means if the p-value p truly is 57%, when I take a random sample of 400, I might get a sample proportion of 51 or whatever it is by random chance alone, and that happens 20% of the time, or whatever the p-value is. So whether we choose to reject or not reject the null hypothesis depends on our p-value. To reject H0, basically our initial assumptions, so if the p-value is small, we will reject the null hypothesis. Basically, we're saying, yeah, it is possible that H0 is true, and that our data happened by random chance. But that probability is so small, probability, the p-value, is so small that I'm willing to ignore it and conclude that my initial assumption is wrong. H0. Okay. If the p-value is large, we do not reject the null hypothesis. Okay, and we would say something like our large p-value tells us that it is very possible or probable to observe our data even if we assume that the null hypothesis is true. Okay? So we don't have evidence to reject the null hypothesis. So I'll let you guys copy that down and let it sink into your heads. Yeah.
Will it always be greater than 0.05?
No. It might be smaller, and that
I mean, like, is it always 0.05? Or
So yeah, let me get to that. The choice of 0.05 or whatever value is, that's known as their significance level, okay? So are these two concepts okay, all right? So many times, the line, so we choose an arbitrary line, okay, where if the p-value is larger, p-value is greater than this, so we choose an arbitrary line called alpha. P-value greater than alpha, do not reject the null hypothesis. And if the p-value is less than alpha, we reject the null hypothesis. Okay? So we pick an arbitrary line called alpha. Alpha is also known as the significance level. Okay? And our most common choice for alpha is 0.05. But you can choose alpha equal to 10%, or alpha equal to 2%, or alpha equal to 1% are all valid. Or any alpha that you want, okay? But alpha equal to 5% has somehow become the most common choice for this significance level, okay? But it's just we're drawing an arbitrary line, and we're saying if my p-value ends up bigger than this, I'm not going to reject. If my p-value is less than this, I'm going to reject. Okay. But again, your choice of alpha is a little bit arbitrary. Okay, and I just want to maybe give you some guidelines as to when you want a large alpha or when you want a small alpha. Okay. I just erased it, but this said when my p-value is small, smaller than some value, okay, I'm going to choose to reject the null hypothesis. We're saying, yeah, it's possible for me to observe my data if the null hypothesis is true. But it's so small that I'm going to just ignore that possibility and say my initial assumptions were wrong. Okay. But what if it turned out that, yeah, you did observe your data on that off, strange probability, okay? So, when you flip a coin 100 times or whatever, you're supposed to see around 50% heads. Maybe you see 30 heads, and you do the math, and it turns out, well, that only happens, 1 in 500 times. So you're saying, the guy is probably not using a fair coin, and that's how he only got 30% heads. But is it possible that he was using a fair coin, and we just happen to see that 1 out of 500 chance? Yeah, it's possible, okay? So, based on the data, you've come to the conclusion that he was cheating or using an unfair coin. But if he actually was using a fair coin, then what we have done is we've made a mistake. We're accusing him of cheating when, in fact, he just happened to get this really unusual thing, okay? And when we go through this hypothesis test, we don't know whether or not we've made that mistake, okay? And how often are we going to make a mistake like that? That's directly related to our choice of alpha, okay? Remember, our p-value is the probability of observing our data if the null hypothesis is true. So that means it's still possible to observe our data even if it's unusual, even if it's smaller than alpha. So we have something called a type 1 error. The type 1 error is our conclusion is to reject the null hypothesis. Okay, so that means because our p-value was less than alpha. Okay, so our conclusion is to reject the null hypothesis because our p-value is less than alpha, but it turns out that the null hypothesis was actually true. Okay? So if that happens, we've made a mistake, and that's called the type 1 error. The probability of a type 1 error is equal to alpha. Okay, so your choice of alpha, if you say alpha is 5%, you're going to make a type 1 error about 5% of the time. If you choose alpha 10%, you're going to make a type 1 error about 10% of the time. Okay, so then you say, well, why don't we just choose a tiny alpha so we don't make a type 1 error? Okay, well then you have the flip side. The other error, we got really creative with the naming, is it called the type 2 error. Alright? And so the idea is if the null hypothesis is true, you don't want to reject it. But if it's false, you do want to reject it. Okay? So if you're